I introduce our next speaker, who is Dr. Anji Seth. She's a professor of geography at the College of Liberal Arts and Sciences at UConn, with funding from NSF, NOAA, NOAA, USAID, and Connecticut DEEP. Dr. Seth's research seeks to understand how and why climate varies and how changes in climate are likely to evolve in the next century in particular regions. Her research employs global and regional numerical climate models. Dr. Seth recently led an assessment of climate change for the state of Connecticut, served on the UConn President's Working Group on Sustainability in the Environment, and is the co-founder of the UConn at COP program, which works with students to build future leaders in climate science and policy. She is currently examining extreme heat events in past and future climates. So go ahead, Dr. Seth.
Thank you, Jennifer. I'm going to start my timer here. Okay, well, thank you for inviting me to talk to this important science boot camp for librarians. I am so happy that you are doing this focus on climate change and sustainability, because you are so central and connected to everything that goes on at your universities. And so having an interest in and the ability to talk about climate with all the different people that you interact with is really important and encouraging to me as a climate scientist. So I want to thank you for expressing that this is important to you. So I have a picture here that's in the background of my initial slide that I just kind of plunked in at the end, and it's a recent picture that expresses the temperature anomalies, so the differences from the long-term average over the last 2,000 years and 2,020 years. And so you can see that the blue colors that are pointing down are negative anomalies. So Earth was cooler than the long-term average for most of the last 2,000 years compared to this average. And the last brief period has been very warm. And I don't know, my video is on top of the end here, so I don't know if I can move that. Oh, shoot, I guess I can't. But in any case, the red goes right up behind the video box. So we are in a warming climate. Temperatures are increasing. And so what I'm going to talk with you about today is a bit of the science of climate change. It is a science boot camp. And also why the problem is so urgent and the opportunities that we have at this moment to really try to solve it. So it's going to be in 3 parts. The first part is about the climate change. So we'll talk a little bit about the history of the science and where it comes from and how we understand the physical science of climate and where we are. And so that's the first part. Then we'll talk about the urgency, then we'll talk about the opportunities. So I always like to start with a brief discussion of the difference between climate and weather. And I know that you are all very sophisticated and you understand this. Most people do inherently, even if they haven't studied it. You know, if I ask, what is climate versus weather? People will say, well, weather is what happens today and climate is a long-term average, right? So that's, I'm guessing most of you would say something like that. And so I'm showing here a typical nice July day in Hartford. And so that is the weather on that particular day. But you could also think about the climate on a nice July day in Hartford. You might expect it to be, you know, warm, either sunny or rainy, but it's going to be, the temperatures are going to be in the 70s or 80s or 90s if you're in global warming. But right now, it's a nice day in July. So what I want you to think about for this topic, though, when we're talking about climate globally, we're not just interested in a particular place. We're interested in the Earth as a whole. And so we're going to think about climate differently. We want to think about climate in terms, and the analogy here is think of a deck of cards. And in that sense, then weather is a particular hand that's dealt from that deck of cards. And so if the deck of cards changes, then the hands that are dealt from that deck would change. So I'm going to try to bring this home. And here is another picture of what a typical nice July day in Hartford might have looked like 22,000 years ago. So Earth 22,000 years ago as a whole was about 6 degrees C colder than it is today on average. And this was a period called the last glacial maximum. There were ice sheets, an ice sheet right here, a mile thick in Connecticut. It ended, the terminus of that ice sheet was Long Island, which is the glacial moraine of that ice sheet. And so clearly the climate was different 22,000 years ago. The deck of cards had been shifted towards lower numbers, and then the weather, or the hands that could be dealt on a nice day in July even, might have looked like this. Now, this is a picture of the Greenland ice sheet, but during the last glacial maximum, Hartford would have looked like this, okay? So climate, when we're talking about the Earth as a whole, really determines what kind of weather we can have in particular places. So it is and it can be defined by Earth's global temperature, global average temperature. So here, I just showed you what Hartford might have looked like 22,000 years ago. This picture you may have or may not have seen before, but it is my pointer doesn't seem to work, but it's a time series, and on the lower right, you have 0. That is present day. So this is years before present going to the left. And so 0 is today, and the going back in time 800,000 years is the time series to the left. So if you want to go forward in time, you read from left to right. And the bottom time series in red or orange, depending on the color on your screen, is showing an estimate of temperature from Antarctic ice core data. So they've drilled cores in the deepest part of the ice sheet in Antarctica, and they can get estimates of temperature from the delta O18, these isotopes of oxygen. So if you look at that time series at 0, there's a short kind of flat period, and that is the last 10,000 years. It's called the Holocene, and it's a relatively stable period in Earth's temperature history. It's when all of our civilization has evolved. And prior to that, that steep decline drops down into the last glacial maximum. So temperatures were in Antarctica, 10 degrees C colder during the last glacial maximum 22,000 years ago. And prior to that, there had been another warm period 125,000 years ago. And you can go back in time and you see this up and down. It's kind of a sawtooth temperature time series from Antarctica. And so those warm peaks are interglacial periods, and the low minima are glacial maxima. So there have been a series of large glaciations, and they have been interspersed with short interglacial periods. And the last one on the right, that's our interglacial, the Holocene. You can also see, and again, don't know how to change where my video is, but behind the video shows where we are currently with CO2 concentrations, and I'll show that again later. But the blue curve is carbon dioxide in parts per million, and also taken from the same ice cores, and you see that very similar pattern. They're nearly identical, and it shows that the carbon dioxide and temperature are in step with each other over this period. And it also shows, which you can't see where we are today, but today's carbon dioxide in the atmosphere, the value in parts per million is far outside this natural range of variability for the last million years. So we have, we know that Earth's temperature changes over time. This happened without us. Carbon dioxide varied without us over the last million years. So we can ask the question, what is it that sets Earth's global temperature? And it turns out that this science was done in the early 1800s. There are some simple calculations you can do to try to get a handle on Earth's global average temperature. And Joseph Fourier, who was a mathematician that worked for Napoleon, did these simple calculations in the 1840s, I think. And so he understood that you can think of the Earth as a rock in space. And if you just look at it very simply, then you can do an energy balance. And the only way to get energy through the vacuum of space is through radiation. So Earth's energy balance is essentially a radiation balance in space. And the radiation sources are the sun, the solar radiation coming from our star. That's the incoming energy. And the outgoing energy is infrared heat. So they're all electromagnetic radiation, but the infrared is lower energy, a lower energy part of the spectrum. And it's essentially heat. So the red arrows represent the heat being emitted by Earth in the form of infrared. And the yellow arrows are the sunlight coming in from the sun. And Fourier just set a balance between incoming and outgoing energy. And you can calculate the temperature of Earth given that. So, and that calculation, if the incoming is equal to the outgoing, gives you a steady state or an equilibrium temperature. So if you want to know what the equilibrium temperature of Earth should be, you can do this calculation and figure it out. But it's a little bit more complicated than that. But this is a really key idea in understanding how Earth's temperature is set. So you can think about it as if you want to change Earth's temperature, or if Earth's temperature is going to change, either one of two things has to happen. Either the sunlight coming in has to change, or the heat going out has to change, or some combination of both. Those are the two key ways that you can change the temperature of Earth. And so where do greenhouse gases come in? Well, again, in the 1800s, in the mid-1800s, there was an American woman named Eunice Foote who was doing laboratory experiments. Now, John Tyndall was doing them in England, and he got a lot more notoriety for that than Eunice Foote did, but Eunice actually did it first. So I like to highlight her. And she showed in experiments, in her laboratory, that if you put carbon dioxide in a vessel and you try to measure the heat passing through that vessel, carbon dioxide will absorb the heat. And it does so, it really does act like a blanket. So the punchline here, I'm not going to go into all of the physics and chemistry of this, but the punchline is that carbon dioxide, when it increases in the atmosphere, will increase Earth's temperature because it reduces the outgoing heat, that infrared radiation. So it changes Earth's radiation balance by keeping more energy in the system, preventing the heat loss to space. Very similar to a blanket. So we already had in the 1800s a pretty good idea that Earth's temperature, is set by this radiation balance, and that carbon dioxide could change Earth's temperature. There was also an understanding that changes in sunlight could change Earth's temperature as well. And it turns out that on that long time scale of the glacial advances and retreats, changes in Earth's orbit are very important to those, but carbon dioxide is as well. So we started measuring atmospheric carbon dioxide in the 1950s. Before then, it was really hard to measure. The instrumentation wasn't good enough. And Charles David Keeling figured out how to measure CO2 very accurately and began his measurements at the Mauna Loa Observatory in Hawaii. So this picture is very classic in atmospheric science and climate, and it shows, beginning in the late 50s, the atmospheric carbon dioxide concentration at Mauna Loa, and it goes right to present day. They're still taking measurements, and now they're measuring in a number of different places around the Earth. But you could see, even in the first less than 10 years, that atmospheric carbon dioxide was increasing. Now, why did they start measuring CO2? Well, we already knew in the 1800s that carbon dioxide could potentially warm the climate. And by the mid-50s, we were burning a lot of fossil fuels, right? And ever more fossil fuels as population is increasing very rapidly. And so there was a recognition that we should be increasing carbon dioxide in the atmosphere. So this question of what would happen as we increase carbon dioxide in the atmosphere became more pressing because we were doing it more and more rapidly. It's a byproduct of burning coal, oil, natural gas. Those are the fossil sources of carbon that basically lock up ancient sunlight deep in the Earth's crust. And when we extract them and burn the fuel, carbon dioxide is released. So we know CO2 should warm the climate by theory. We know from observations that we're increasing CO2 in the atmosphere. And we know from observations that Earth's temperature is warming. So you've probably all seen many maps like this of increasing temperatures. These are observed temperature changes. The reference period is most of the 20th century. And you see that temperatures are increasing everywhere on Earth. They are increasing more on land than over the oceans. And that makes sense because land heats up faster, takes more time and energy to heat up the oceans. They have a larger heat capacity. And you can also take averages for the globe over land and over oceans. And those are to the right, actually. The panels on the right are global average temperature changes from the long term for annual periods and 10-year increments. So you can see that the temperature increases are fairly dramatic over the 20th and in the early 21st centuries. So there's no question that Earth is warming. That has been called unequivocal by the scientific community. And we can also see the effects of warming everywhere. So the Northern Hemisphere, springtime snow cover, ocean heat content in the upper oceans, sea ice extent. There's a lot of discussion about in the Arctic and the impacts that's having. and sea level. So these are just 4 of the indicators. There are many more. Our previous speaker talked about the health indicators that are showing, everywhere you look, you see the evidence of a warming climate. So there are many, many independent lines of evidence. So we have this history and this understanding that Earth is warming. We know why. It's because of carbon dioxide. So how can we project the future? Well, we can use past climates and our understanding of that to have some ideas of the climate sensitivity of the Earth system and have some suggestions of future temperature changes from that. We can use simple models, but the work that I have done and that, hundreds of scientists around the world have been developing climate models to do scenario projections of the future. So the way we do that is we have to have some estimate of the radiative forcing of the Earth, right? So we said that Earth's temperature is set by this radiation balance in space, the sunlight coming in, the heat loss to space. So anything that affects that radiation balance has to be incorporated in the model for the long-term projections. And carbon dioxide is one of those things because it prevents the heat loss to space. But there are other things as well. And anything like volcanoes, land use change can change the reflectivity of the Earth. So all of these things are incorporated in our climate models, and estimates are made for the future. So because humans are the primary cause of these changes, it really depends on what we do, how things are going to change in the future. So it's our choice, and I'll show you that now. So these are just, I'm not going to go through details here, but there are socioeconomic pathways that have been developed that they provide I've written it up here, they provide a consistent set of assumptions looking to the future about economic development, cultural changes, technological developments, and all of those wrapped together then can give us a sense of what will happen in this particular pathway in terms of CO2 emissions. And the CO2 emissions then, along with some other things, give us the radiative forcing on the climate system. And so those are the 2 panels given. There are some scenarios that have very high radiative forcing and a lot of CO2 emissions, and some pathways that have very low radiative forcing and CO2 emissions. So you see that they're closely related. So we take these scenarios and we run climate models with them, and those scenarios can give us a bracketing of what might happen to the climate system in the future. This picture is kind of simple, but it tells a lot. It's just the global average temperature of Earth starting in 1850. The black line starts in 1850 and ends in 2000 approximately. And then there are colored lines that continue from 2000 out to 2300. And the vertical axis is the global surface temperature change. So you can see that from 1850 to 2000, the temperature of Earth was below 0. So, that's, if you take the long-term average, then Earth has been a little bit cooler over the last 150 years. And then over the next 100 years, it is warming, right? It was warming from the 1950s as well, but it's warming even more. And you can see that the changes in the 21st century out to 2100 are much bigger than what we have seen so far, right? What we have seen so far is about 1 degree C increase. And we're talking here about the low scenarios are less than 2 degrees C, and the higher scenarios are more than 4 degrees C. So these are global average temperatures, and I know that they're kind of hard to interpret. You're like, oh, 2 degrees C, 4 degrees C, what does that really mean? You know, it changes more than that from day to night. So I like to show this set of maps because it shows the distribution of temperature and how that distribution evolves over time. And so what I'm showing here are the change in temperature, and you can see that most of the temperatures here are in the yellow and red, so that means increasing temperatures. In the left-hand column, the panels are showing the 2050s, the middle panel is the 2090s, and the right panel is actually like 2190, so it's in like another 180 years, okay? So we see that the top panels are the low CO2, low radiative forcing scenarios. And they show some warming, but they don't show a continued warming. The warming kind of levels off by the 2050s and maybe even gets a little bit less in 150 years from now. In the high CO2 scenarios, that's where we kind of keep burning a lot of fossil fuels. The 2050s are already significantly warmer than the low emission scenarios. And then, but then in the 2090s, it's warmer still. And in a couple of 100 years, we've got some very significant temperature changes. I mean, I would argue that all of these temperature changes are significant, but it starts, those colors start to look a little scary going out into the future. So the point here of these scenarios, first of all, is that the temperature changes aren't distributed evenly. If you look across the globe, right, the high latitudes are changing much more significantly than low latitudes. But even in the larger changes, the continents are much hotter than the oceans. And so this is not an even distribution. We also see from these experiments that it is possible to keep temperatures less than 2 degrees C in these scenarios. It is possible to do it, you know, scientifically in these, given the assumptions made. And it also shows that in the scenarios that are heavily reliant on fossil fuel development, the Earth's temperature does not stabilize even by 2300, the year 2300. So Earth's temperature is continuing to warm. The more CO2 we put in the atmosphere, the more warming we get. Okay? The other really important scientific outcome from our last assessment report, and there's a new one imminent now, but this was really key, and it's important to the discussions of what we're going to do about this. And that is that what matters for temperature, for global average temperature, is the cumulative human-derived carbon dioxide in the atmosphere. So, and that's what this plot is showing. It's showing from, it's actually showing the cumulative emissions of carbon dioxide in gigatons of carbon since 1870. So that's the x-axis. The y-axis is showing temperature change relative to the 1861 to 1880 period, so pre-industrial temperature. And then the dots with the colored lines, the black shows the actual observed, so we know pretty accurately how much CO2 humans have been putting into the atmosphere since industrialization. and those little dots, black dots, tell you the years and the amounts there. So by 2010, we've put in a little bit less than 500 gigatons of CO2 globally. And then the colored lines show these scenario pathways. So there's a dark blue pathway that says that by 2100, we would only emit, let's say, 800 gigatons if you drop down there. There's a red scenario that says, oh, by 2100, we're going to emit more than 2,000 gigatons. So there's a large range of possibilities for what we might do. But we see that there's an almost linear relationship between how much CO2 cumulatively we put in the atmosphere and how much temperature change we get out of the system. So if we want to, say, limit warming to 2 degrees C, which is what the scientific community and the international negotiations said in Paris in 2015, we can look at this plot and say, oh, 2 degrees C, and you come across from 2, and then you drop down and you say, okay, from 2, we have to be somewhere around 850 gigatons of carbon. That's our carbon budget globally. And that helps us understand, oh, I am so sorry. I don't know what just happened here. I turned off notifications and I hate Adobe. I am gonna just try this again. Oh, shoot. Here it is. Sorry about that. I thought I turned off notifications. Okay, anyway, so if we want to keep warming to less than 2 degrees, we can use this, and this will help us set policy, right? So it's a kind of a brilliant tool to estimate what is needed by when in order to limit warming to a certain amount, okay? And so that leads us, let me just summarize this first part here. I think I'm doing okay. This first part here. So Earth's temperature, we said, is set by the radiation balance. That's the incoming sunlight and the outgoing infrared heat to space. We said CO2 warms Earth's temperature because it reduces that heat loss to space. And we know we're adding CO2 at unprecedented rates, very rapidly. So, and we also know that Earth's temperature is increasing. So there's unequivocal warming. And all of these things make a package to say we understand why Earth is warming. It's because of us. Now, it further tells us, the projections says we're choosing right now how much temperature change we're going to see in the future and how quickly temperatures stabilize. In fossil fuel development pathways, we would have much larger changes and potentially very unmanageable impacts. In sustainability pathways, we can achieve a less than 2 degrees C world. It is possible. And I'm going to get to why, but to limit warming to much less than 2 degrees C, it will require pretty near zero emissions by 2050 because of this carbon budget. So we have this Paris Agreement we've all heard about. In Paris in December 2015, the international climate negotiations, there was a unanimous vote that said that that countries would hold the increase in global average temperatures to well below 2 degrees C, above pre-industrial levels, and further to pursue efforts to limit the temperature increase to 1.5 degrees C. So well below 2, but shooting for 1.5. So then the international community went to the scientists and said, okay, we just did this. Now will you tell us what is the difference between 2 degrees C and 1.5 degrees C? What are the difference in impacts? So the scientific community went to work and wrote a new report that was the 1.5 degrees C report. So this is where we get into the second part, and I'm going to go rapidly through this because I'm running out of time, but the urgency. So what is the difference between 1.5 and 2 degrees C? Well, we've got these reasons for concern. So we have the physical science, but we can look at the impacts of temperature and rainfall changes. And this kind of a diagram used by the IPCC shows the reasons for concern. And these are like the big reasons for concern: unique and threatened systems, extreme weather events, the distribution of impacts, etc. So the way this works is there is a gray bar that shows 1 degree C of warming, and then a line that depicts 1.5 degrees C, and another line higher that depicts 2 degrees C. The colors in each bar identify the level of risk for these systems. And so yellow is moderate, red is high, purple is very high risk for this amount of warming. So you can see that unique and threatened systems and extreme weather events and the distribution of impacts are already in moderate risk. And as you get to 1.5 degrees C, those go to pretty close to high, if not high risk, and into the purple at 2 degrees C. So there is a difference in the amount of risk for these systems between 1.5, and 2 degrees C. And that was one of the big outcomes of this analysis, because initially we thought, oh, what's the difference between 1.5 and 2? But when we actually, the scientific community looked at it, they found there's actually a big difference. It makes a difference. Every 1/10 of a degree C of warming adds more risk to different kinds of systems. And so this picture is the same, but it breaks things down into particular types of systems. So warm water corals are already in very high risk, right? The Arctic region. And then they have heat-related morbidity and mortality that our previous speaker was talking about to some extent. So the punchline here is that the difference between 1.5 and 2 is very meaningful, and everything we do to limit CO2 increases will have an impact. So there's no point at which we can say, oh, you know, we've crossed this threshold, we're not going to worry about it anymore. If we miss the 1.5, we'll try 1.6. If we miss the 1.6, we need to try for 1.7. You know, it will make a difference because there are different systems that are going to be threatened at higher risks. And I think Mike Wheeler will talk about this as well. So one other thing that is really critical in terms of urgency is sea level rise. And some of the evidence coming from the scientific community that studies Earth's past climates is really amazing. I'm not going to go through this picture in detail, but the punchline here is that if you go to these periods, these previous interglacial periods, and you get the evidence of what sea level looked like then, the amount of CO2 in the atmosphere was similar to today at 400 parts per million, but sea levels were 10 to 30 meters higher. So today we have a value of carbon dioxide in the atmosphere that has not been seen for at least 3 to 5 million years in the past. And at that time period, sea levels, when they were equilibrated, were 10 to 30 meters higher than they are today. So that's a pretty key piece of information. We don't know how fast Greenland and Antarctica will melt, but we do know that at even the current levels of CO2, we're in for a long thaw. So the 1.5 report has basically established this 1.5 degrees C as the new target. You know, from Paris, we were talking about 2 degrees, a little bit less than 2 degrees, but really this is telling us we need to shoot for 1.5. We should put everything we can into trying to limit warming to 1.5, because above that, we are going to see more and more risk. And so we can look at where we are internationally. This thermometer from the Climate Action Tracker tells us, you know, where the Paris Agreement 1.5 goal is and where we are currently with pledges, current policies, and optimistic targets. We have a lot of work to do. And to achieve 1.5, we really have to get globally to net zero carbon. And I could talk about net zero. I hope one of you will ask me about it, but really zero carbon by 2050 is what we have to think about. Okay, so I just ran out of time. I'm gonna, and I can't stop this for some reason. So if I can just take one more minute to talk about the opportunity, because it's so important. We're in a critical moment right now where we have an alignment of youth activism, so many different groups that are seeking environmental justice, racial justice, and we see how intertwined all these things are. So there are movements underfoot that are really helping us to make progress on this issue at the moment. Because the US is the largest emitter historically, we have the most cumulative emissions, which are the important measure here. It's up to us to lead on this issue. The US must lead, and we should achieve zero before 2050 if we can. And we have the technologies right now to get to 80% reductions. You know, it's really a question of will, not technology. So we can electrify everything as soon as possible. There are lots of reports out there. This one is from the Rewiring America organization, and it shows us how we can do these things and what the financing would be. Most American households would save money if they did these things right now in the next few years. It is possible to electrify our heating and cooling, our cars, our water heaters, you know, anything that we burn oil or gas in, we can change. And we need to update the grid. And there are plans in the Biden administration, the Lamont administration. Many states are planning this already, so we have momentum. And finally, this was from the New York Times, that shows how much wind and solar is going to be needed by 2050 to do this. And it's pretty shocking compared to how much we have right now. So there's a lot of work to do. And I guess I'll leave it here with a couple of items that say, you know, point you to excuses for climate inaction and how to refute them, and this International Energy Agency report that gives us a roadmap to 2050. So thank you.
Thank you, Dr. Seth. All right, so we have some questions coming in. All right, when communicating the harsh realities of possible climate change futures, how do you foster in your audience a drive to make the changes necessary rather than a sense of despair or fatalism due to the difficulty of, you know, building that international will to actually make things happen?
Yeah, I know, that's a great question. And I guess I could ask I could ask the questioner, how did I do? It's not always easy because the news has been so terrible. and the science is so clear. But as a climate scientist, I go through my own despair and my own like, oh my goodness, how are we going to do this? But right now, I am more optimistic than I have ever been, and I hope that that came through in my talk. We are really at a critical moment. We have what we need. We can't be defeatist about it. We have to get everyone on board and everyone like just doing what, everyone has a role to play. I'm not saying that individual like carbon footprints are going to solve this, because they're not. We need systemic change, but everyone has a role to play in that systemic change. And so, we have to be talking about it as much as we can.
Yeah. So kind of talking about the individual carbon footprint a little bit. Another question from the audience about, scientists like yourself, researchers need to travel, including traveling internationally to do your research. And the question is, what do geoscientists consider the best methods for making carbon offsets if that travel is necessary? Some conferences are shifting to virtual, saying that air travel is not sustainable. So what do you think about that? Or, what do researchers consider the best way to do carbon offsets?
Yeah, I think, I think you'll get an array of answers from people on that. I know people who buy offsets and they, do a lot of research to find reliable offsetting companies. My personal opinion is that I am very distrustful of the whole process. And so I have done a lot of flying. My personal footprint has been terrible in the past. The pandemic has allowed us to like do all of this virtually, so we don't have to fly. And I'm very happy about that. So I would love to do a lot less traveling. And I guess what I would say is, if you are going to purchase offsets, if you have to travel, do the research to make sure that you're not just, paying to make yourself feel better, right? You want to make sure that those are going to be real, long-lived. If it's not going to sequester carbon for 100 years, don't put money into it, because otherwise it's just a scam. So I think it's better to like not feel good about it and find ways to reduce your travel than to, pay somebody to feel good about it.
So I see you have a thing about net zero emissions on your slide. So that relates to another question that I have. So what does net zero carbon emission really mean, and how likely is it that we can actually achieve that?
Yeah, so that's thank you for asking that. So net zero has the most meaning at the global level. When scientists talk about net zero by 2050, what we're talking about is globally the emissions from humans must be balanced by whatever things are removing CO2 from the atmosphere. So that means that there is no net new carbon dioxide going into the atmosphere. And I'll just take this moment to note also that when we talk about 2050 and net zero, whatever, that is not the end of the road. That is the midpoint. Getting to zero, getting to a balance between what we're putting in and what's coming out, is all that will do is it will stop the increase of CO2. After that, we will very likely have to remove CO2 from the atmosphere to try to keep temperatures below 2 or 1.5. And so there's a long road ahead of 2050 with a lot of work still to do. But the net zero is a meaningful term at the global level that says that there's a balance between what we're putting in and what is being taken out by natural sources and any other mechanisms, whether it be, carbon sequestration by, mechanical means or from trees or agriculture, but all of those things are very tricky to measure and to actually implement. They're also sequestration from mechanical means are expensive. So we don't have means to do that effectively at price points that can be done at this time. And so if you project out and say, oh yeah, we're just gonna remove all that CO2 later, that's not a good way to do this. It's the cumulative carbon that matters. And so every CO2 molecule you can save now from putting into the atmosphere is going to reduce the warming from now until 2050. So earlier reductions are better because it's a cumulative problem, and real reductions that have a meaningful impact on the global carbon budget. So if you have a company that says, oh yeah, we're net zero, we're paying for these offsets, I would not buy into that. I think Shell has put out a report saying that they're going to be net zero, but they would need forests 3 times the size of Brazil to do that. So be critical about these evaluations of net zero. Net zero is a globally meaningful term. We shouldn't be using it so much for individual companies or our own carbon budgets. We should be reducing the carbon.
Okay, thank you. That's a good way to explain those terms and get us a grounding. So switching directions a little bit, one of my other hats is also working with data, researchers on their data as a data librarian. So there's another question here. If you could talk a little bit about the programs or platforms that you use for modeling big data. What are the common ones that are in use in the field, or why are certain things used over others?
So that's a really big set of questions. So numerical climate models, the big comprehensive ones that include atmosphere, oceans, land, ice, those are run on the biggest supercomputers in the world. So, the National Center for Atmospheric Research has a supercomputer in Wyoming, and the Department of Energy labs have supercomputers in a couple of different places. And so when these climate model projections are being run, they require, probably like 6 months of computing time for one set of experiments on the fastest computers in the world. And I'm not even as up to date. I used to run the models myself, but my students now would be able to tell you more detail about the details of the computing infrastructure, but they're, the biggest exascale computing out there. Yeah. There's also, because the grid size of the grid cells in the models are getting smaller, so there are more and more, grid cells, more resolution in the models. They're like 1 degree or less, so you could just say 360 by 180 grid cells on the Earth if it's 1 degree. And so you have to have calculations and data for all of those grid points, plus vertical levels in the atmosphere. So it's a lot of data, and the models are calculating that data in time every few minutes. So if you do an experiment from 1850 to 2300, that's a lot of years, and calculations every few minutes, and output model data saved every hour or every 6 hours. So we're talking, terabytes of data very easily. And so how you process that data, it used to be that I could go and download, 5 models worth of data and put it on my computer. Now you can't do that anymore. It's all like cloud computing. You have to you can't download that much data, so you're doing the calculations up there and then bringing what you can locally to process. So I don't know if that is answering your question, but we use Python, we use a lot of scripting tools. The models themselves are written in different kinds of languages, but Fortran is the base coding for climate models. It sounds crazy, but that's really what it is.
Thank you.
Yeah.
So we can probably squeeze in at least one more question. So in your experience, what are the most effective means of convincing skeptics of the reality of climate change?
Oh, that's you guys.
In your experience.
Yeah, the skeptic question is really good. And I have, I've been talking with people about this for 30 years. And so, you know, some people I have convinced and others you just can't, you know. And I'll just say, my dad was one of those people. You know, he passed away a couple of years ago, but it was one of those people that was just, even though his daughter was a climate scientist, was not going to buy into the fact that humans could be changing the climate. So, so some people you just can't get to, but most people are open. And I find that if you talk about the science, and it's irrefutable, really, to most people if they see it. But you know, there's a lot of discussion about communicating climate and saying, oh, well, just stay away from the science, stick to the moral issues or the psychological heart issues. You know, there are so many different ways to reach people that don't necessarily involve the science. And I'm not an expert at that because I talk about the science, but there are many different ways to do it. And I think the key is to talk openly and be inquisitive and not just like point fingers and say that you know everything, although that's kind of what I do because I do know everything.
Right.
I don't know everything. Sorry.
Nobody knows everything. All right. Do we have any other questions from the audience? We have another moment.
I had one more slide that was going to show the Yukon President's Working Group for Sustainability in the Environment, but Patrick talked about that already and I was late.
Great.
So
no, that's great. Yeah, Patrick covered a lot of that stuff too, so that was great. All right, so I think there's no more questions coming in. Yeah, so thank you, Dr. Seth. We appreciate you being here. Thank you very much.
Should I stop sharing my screen?
Oh, you can stop sharing. That was very interesting. So thank you again for your time.